And so when you're taking a look at this, remember the very first step that you'd want to do is you'd want to rewrite your function here as a series of individual terms. So like I would take the 3x squared over x squared. What's 3x squared over x squared simplified down to be?
3.
Yep, just 3. And then I'm going to do minus the 5x over the x squared. Well, the 5 would still be on top, but I'd still also have an x on the bottom, so it would be 5 over x. Of course, even that's going to be tricky to find the derivative, right? So then, rather than writing as 5 over x, I could then write that as 5x to the negative 1. And then repeat the process with that last one. So plus, it starts out as 1 over x squared, but then I rewrite it just in polynomial form. I get rid of the fraction, because of course we can't find derivatives of any fractions yet. And so then that becomes x to the negative 2. And now we can actually start finding our derivative. All right, so we go term by term here. What's the derivative of 3?
0.
0. So that's gone. So next up, I'm going to do the derivative of my negative 5x to the negative 1. So I do the negative 5 times the negative 1 exponent. So that's going to give me a positive 5 then. And then I subtract 1 from the exponent to use power rule. And so negative 1 minus 1, remember, is negative 2. All right, and then we repeat the process for the second one, where we end up with a negative 2x to the negative 3. All right, and so that is now our derivative. But you'll notice we're not quite done with this one, because it does say to write our answer as a single fraction. Yes, we're now going to be simplifying as we go. And so you'll notice then I can turn them both into fractions then, right? So this would be like 5 over x squared minus 2 over x cubed. Notice the x's move into the bottom, but the numbers don't, because the numbers don't have negative exponents on them. So they stay in the top there. All right, but then they're now both fractions, but I need to make it a single fraction, which means I would need like a common denominator in order to be able to actually add the fractions, or in this case, subtract them. So then I'd make them both into x cubed. So this first one is going to be 5x over x cubed. And the second one's already over x cubed, so that's going to be 2 over x cubed there. Now that I've gotten that far, I can now go ahead and do the subtraction, turn it into a single fraction. So we end up with 5x minus 2 on the top and an x cubed on the bottom. Now, before we go on, I do want to point out that there was actually another method that you could have used to do this particular problem. What if I had instead written this as f of x equals my 3x squared minus 5x plus 1 times x to the negative 2? We could then do that derivative using which rule? Yep, we could use product rule at that point. So original times derivative plus derivative times original, and we could have done the same thing that way. And after simplifying it all through, as we saw before when we first learned product rule, we still would end up with something that's equivalent. So yes, that would still work. But wouldn't it be easier if we had like a quotient rule or something like that, right? Because that's really what this problem would ask for, is like a quotient rule, where quotient, of course, meaning the result of division, so something that would allow us to divide a function by a function like that. And so that's what we're going to be doing today and actually this week, is focusing on learning the quotient rule, which should start by going into your derivative rules notes. And yes, this goes specifically on that special derivative rules page. Now, one thing that you'll probably notice here compared to product rule is that this formula is not only bigger, but it's going to be more finicky too. Because you'll notice that in our numerator here, it's subtraction. So the order is going to matter. So it's going to matter which one are we finding the derivative of first, and then which one are we finding the derivative of second. And of course, it also going to matter which one is on the bottom, because you'll notice that it's the bottom function, the denominator function, that we're going to be squaring on the bottom as well. So let's dig a little bit deeper into this. First of all, this is a nice way to remember it. This tends to be a short way to write it here with the G's and the F's like this. But technically, we'd be better off. This is the technical way of writing it, where we'd actually have like the d over dx in there. That way we actually have the f of x's, and we aren't shorthanding it. But you can see why I didn't give this to you the first time, right? Because when we look at it this way, it just looks like a mess. And of course, you notice that in the formality we also have to state that this works as long as f and g are differentiable. If we can't find the derivative of f or the derivative of g, then all bets are off. We can't use it. But this is the same thing. But one nice thing about noticing this particular notation is that it actually gives us a nice way to be able to remember this. Because of the d's in there to represent the derivatives, there's actually a way that we can remember this, kind of one of those phrases that we can remember that helps us to memorize certain formulas, and this one's well deserving of such a thing. And so I'd recommend that you be writing this part down so that you're going to remember how we can do this. Because if you can remember low d high minus high d low over the square of what's below, you're going to be able to remember quotient rule. So add this also into your notes here so that you'll be able to remember this. And of course, the nice thing about this way of memorizing it is that it's a little bit of a rhyme. So it's also going to be telling you if you did it right. Because you'll notice low d high minus high d low, and then that's all over the square of what's below. So you'll know if you messed up that top part because it won't rhyme anymore. So just by knowing this, it's going to help you to keep all this straight and to be able to know and memorize the quotient rule here, which of course we're going to need to know going forward. All right, so now to practice using the quotient rule, we're going to go back to that same problem that we did at the start of class, and we're going to find the derivative of it once again, but this time using the quotient rule. All right, so for using quotient rule here, because I am using quotient rule, I'm going straight to the derivative function in this case. So I'm not starting with like an intermediate f of x function that I had to write a certain way, and go ahead and deal with it as it is. And so on the top of this, we're going to do low d high first. Low represents the low function, the function that's on the bottom at the start. And so that's just going to be x squared. And you can put parentheses around that or not as you wish there to help it look visually easy to follow. So that's low. Next up is d high. So the derivative of the high function, the derivative of the function on the top. So then that's the derivative of my 3x squared minus 5x plus 1. So that's going to be 6x minus 5. So that's low d high. Now minus, notice it's minus with quotient rule, not plus. Minus high d low. So high, that's whatever's on the top, left exactly as it was, no changes to it. And then d low. So the derivative of the function on the bottom, the derivative of x squared is 2x. And so that's our top. Next, on the bottom, it's all over the square of what's below. So that means I'm going to take whatever is on the bottom and I'm going to square it. In this case, what's on the bottom is x squared. And this technically right here is the derivative. So we've done it. It's just that right now it's not very pretty, right? A lot of functions will actually be able to just leave like this kind of a thing. But for this one being all polynomial, I want us to simplify it. In fact, I want us to simplify it and prove that it does in fact equal the same thing that we found earlier. So now that we've figured out what our derivative is, now just simplify it, please. And the first thing I'm going to do with this is I'm going to distribute, but you'll notice I didn't just totally get rid of all of the parentheses here. There is a potential pitfall if we aren't careful in dealing with the minus here. And so you'll notice I multiplied the 2x into the 3x squared minus 5x plus 1 to get this. But I left it as minus the parentheses just so I don't forget that that subtraction is applying to the entire parentheses, and it's going to be flipping the sign of everything that is inside of it. If there's going to be any mistake made on these, it tends to be a sign error due to that. So just be careful with that part and keep working from there. Now some of you, it would be a great idea to go ahead and just show what would it look like only if I distribute in that minus. Others of you, you're just going to say, okay, so now I'm going to be doing 6x cubed minus the 6x cubed, and you're just seeing that it's that minus being applied there. And then when I do the negative 5x squared, I'm doing minus the negative 10x squared, so that's going to give me a positive, and then it's going to be subtracting the 2x. Some of you are going to keep track of that stuff really well. Some of you are going to have trouble keeping track of it all. So just do whatever you have to do, even writing out an extra line, in order to be able to track all of that little detail. If you do that correctly on the top there, the whole top should end up just being 5x squared minus 2x. And at the moment, this is all over x to the fourth. This is still not the same as what we did earlier, but that's because we can still simplify it a little bit, right? Because in order to simplify a rational expression like this, I look to see what can I divide out of every single term, and you notice they all involve an x. And so if I now go ahead and cancel out x's out of every term, I end up with what we found earlier, the 5x minus 2 all over x cubed. And so yes, it does give us the same answer. They are equivalent. It's just different ways of getting there, different formatting in order to get there, some little details like that. The nice thing about quotient rule, though, is that the quotient rule is going to allow us to be able to find some derivatives that we wouldn't have been able to do otherwise. Because like in this example that we were just running through, these were polynomials. I could simplify it first. That's how we did it at the start. But we're going to be seeing a bunch of other ones where we would, strictly speaking, have to use the quotient rule. For instance, if it was e to the x over sine, we would have to use quotient rule. But there's even some polynomials, even polynomial on both top and bottom, where we'd still need quotient rule. So that's what I want to take a look at next, is recognizing when do we and when don't we truly need to use quotient rule. Because sometimes people think it's a messy formula and they'd rather avoid it. So let's see, which of these up here would you have to use quotient rule for? All right, so taking a look at these, like for that first one, f of x, we have x plus 1 over x squared plus 1. Well, if I was thinking about, well, what if I try to split it into multiple fractions? Then I would have x over x squared plus 1 over x squared plus 1. That didn't really help me out, did it? I didn't have any other way that I could actually simplify that down further from there. Is there anything else I could do to that that would allow me to like just turn it into a straight polynomial without division? Not really. It doesn't work so well. And in fact, let's actually take it one step further, because I think somebody might be thinking of this one. If you're thinking really out of the box here, you might have come up with this, which would actually be pretty cool. You might have thought x plus 1 times x squared plus 1 to the power of negative 1. But this actually has an inherent disadvantage that we haven't even looked at yet, because what you actually have here is you have this function inside of this function. And there's actually a totally separate rule that we're going to be learning later on that allows us to deal with a function within a function. But because it is a function within a function, we cannot do it. And so because of that, this one, the only way to find the derivative is with quotient rule. There would be no other way around it. All right, what about the next one, g of x? Would that one require quotient rule? All right, so in this case, yeah, we could break it up into two separate ones, and notice each of those would reduce and simplify, and so we could actually do that one using the skills we already had. So for g of x, yeah, it does not require quotient rule. So for this one, you could have found it. You could have found it just using, let's say, power rule. Would have been fine. But you also could use product rule in that kind of situation as well. All right, h of x. Could we do it without quotient rule? Well, for h of x, I could turn both of those into like x squared over 5x, and then x over 5x. we could simplify those. We could find those derivatives. In fact, that one would end up being pretty easy because there wouldn't even be any fractions hiding inside of it after we simplified. And so, yeah, we don't require quotient rule there. Now, could we use quotient rule? Yes, we could. However, you don't need it. All right, j of x. Do you need quotient rule for j of x? Yes, we do. Now, it's actually pretty close to not needing it, but it does need it. Oh, we've got to switch over there. There we go. And so, yes, we do need quotient rule for this one. All right, k of x. For k of x, yes, we would need quotient rule there. So, for k of x, we would need quotient rule. For m of x, would we need quotient rule for that one? Well, this one's actually getting a little bit tricky, making you think about it a little bit more, because you'll notice that x squared minus x, that factors, doesn't it? And so that can become x minus, oops, that's a minus there, x minus 1 over x times x minus 1. And if I simplified that, the whole thing would just simplify down to be 1 over x, which we can find the derivative of without having to rely on the quotient rule. So m of x, you don't actually need quotient rule. Look for things that you can simplify first. So then, what about n of x? Do we need quotient rule for n of x? Well, again, I do see something that's factorable, so I'm going to go ahead and check that factoring first, because the top, the x squared minus 1, factors. That would be x plus 1, x minus 1. And all of this is over x plus 1. Well, notice I now have x plus 1s that cancel. So really that whole thing is just equivalent to x minus 1. Can I find the derivative of x minus 1 without quotient rule? Absolutely. And so you don't even need it for that one. So notice, quotient rule is very useful, but it's not needed every time you see a fraction. You do have other options available. Now, anytime you see a fraction, you can use it. Just realize you don't have to. All right, now for some of these, we did need to use quotient rule. So I want to practice with some. So here's that same f of x, the very first one that we talked about. I'd like you to please find the derivative of this, which we would not have been able to find any other way. All right, so we do need quotient rule for this, so let's go ahead and use quotient rule. So we're going to do f prime of x straight away. So low d high, so low is the x squared plus 1. D high is the derivative of the function on the top. The derivative of x plus 1 is just 1. I'm going to go ahead and write the 1 there, though, so I remember that I actually thought about it and actually did the derivative to get that. Minus high d low. So that's going to be the x plus 1 times the derivative of the bottom. Derivative of x squared plus 1 is just 2x. And that is all over the square of what's below. So I take whatever's on the bottom, the x squared plus 1, and I square that. I found the derivative. I'm actually done at this point. I don't have to do anything else, but I'm guessing that we did continue on there because it is always good to simplify down a little bit further, especially something that looks as ugly as that did. So then I could go ahead and distribute, so that'd be x squared plus 1, and then minus 2x squared minus 2x. Watch those signs. And then, yeah, let's go ahead and square that out on the bottom just to remember what that would look like, because that would be x to the 4th plus 2x squared plus 1 on the bottom. Remember that when you're squaring a binomial like that, you can't just square the x squared and square the 1. You actually have to multiply x squared plus 1 times x squared plus 1. All right, so then we'd have f prime of x equals negative x squared minus 2x plus 1. All over the same thing. And since this is as simplified as it will get, because there is no other factoring we can do on the top to cancel anything out on the bottom, we're done. This is even the simple version of our derivative here. And again, notice we could not have found this by any other means that we've had so far. All right, so from here, this is one of those problems that we were looking to see that we needed to use quotient rule. We're going to do one more of those we saw earlier and saw that we needed quotient rule. we're going to do the k of x. So please find the derivative of this equation now. All right, so for using our quotient rule here, k prime of x is going to equal low d high. So that's going to be x squared minus 1 times 5 minus high d low. So that's going to be the 5x times the derivative of x squared minus 1, which is the 2x, all over square of what's below. So x squared minus 1 squared. And again, that is our derivative. We've actually technically done the derivative there, but of course we just can't help ourselves. We want to be able to simplify, especially something that looks like that. So if we do some distributing here, 5x squared minus 5 minus 10x squared. And I'm just going to go ahead and leave this factored on the bottom. It'll actually make it easier to figure out if there's anything that can cancel later on if we get opportunity to. And so on the top then I end up with a negative 5x squared minus 5 all over the x squared minus 1 squared. All right, does that simplify anymore? Well, I could factor a 5 out of the top, right? Would that help us? Well, it looks close to it. If I did that, I'd end up, if I factored out a negative 5, I'd end up with x squared plus 1 all over the x squared minus 1 squared. Close, but not quite, right? Because it's the plus 1 on the top and the minus 1 on the bottom, we can't quite cancel. So we almost were there with being able to reduce it and cancel it further, but we just couldn't. So that actually is as good as it gets.